another draft physics video presentation. Hell with that welcome part. Anyway, I don't know why I said that. Habit in other places. Anyway, yeah, I already made this video, but Linux failed me. Again, it's still doing this stupid thing where it doesn't pick the right output device and blah blah blah. So anyway, it didn't record with the microphone. So that didn't have any sound on my whole video, and that was just too depressing. But anyway, it happens. I have to do certain, tests to make sure things are working before I make a video. It's just annoying. Anyway, really shouldn't have to, but it's better than nothing. I mean, this is pretty good technology. Just isn't completely reliable, dependable. So anyway, alright, so this is a Dr. Becky video. It's just sort of annoying, this whole, trivial way of looking at expertise. And so she's supposed to be an expert. That's what doctor's supposed to mean, is that you sort of know something. And this video is so bad. The history is all wrong. She says it's one of her favorite subjects, and she doesn't have any of it right. I mean, it's just wrong everywhere. Everything she says is wrong. It's just wrong, 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 wrong. So I'll play it, and it's just horrible. And nothing against women, but I guess, if they're going to stand up and play, they ought to play a lot better game than this. This is just really rubbish. 82,000 views, only 55 dislikes, and again, it shouldn't be disliked for any other reason than it's got so many errors in it, and it just shouldn't be standing as any kind of physics video. And like I said, for a doctor to make this is leg bone connected to the ear bone or something. I mean, it's just so bad. I mean, doctor. So her doctorate apparently is in cosmology, which is, a pile of crap. So anyway.
So 2020 is the 100th anniversary of something that's been dubbed the Great Debate in Astrophysics. And to celebrate, I figured all this month I would do a series on some of the biggest debates ever in physics history.
All right, let's understand. There wasn't any great debates. They're always between individuals and closed doors and all of this kind of stuff. It's not any kind of open debate. It's not open to, hey, did somebody see something that we didn't see? This is the real problem with how things are done. It should be open in court. We should examine all of this stuff, and it's not done that way. So it's a very isolated debate in an isolated forum, and all kinds of wrong things can happen as a result. The wrong side gets to win.
Starting with the debate that saw Einstein and Bohr facing off for most of the 20th century. Science
that isn't really true, but whatever.
After all, is a debate, right? Like, the scientists are the jury, and you have evidence like for and against.
The scientists are the jury. Well, again, they're not really, because they don't hear any of the evidence. All they hear is the stories told. And so, again, there's no real, going through the evidence and analyzing it and testing it, banging the evidence against, a wall. Trying to see if it falls apart, if it's just a facade, if it isn't a real gun, if it's a plastic gun, if there ain't bullets in it, jelly beans. I mean, these are important facts, and none of the facts are important in any of these debates.
Against different scenarios. Often that evidence isn't complete, though, and we're just working with what we have at the time. But over time, as more evidence is found that overwhelmingly supports one idea over the other, that's when we settle on accepted theory. Now,
yeah, whatever. You're doing it wrong. Okay, just because you have chosen badly over and over and over again. So clearly your process of discrimination is really, really bad. And you do draw conclusions. Your carts are way ahead of your horses. You jump sharks. You jump the evidence. You are leaping to conclusions. Seems like, is like. I mean, all kinds of just fundamental mistakes. And even the classic discipline you're supposed to have, where you say, let's repeat it. Let's do it over and over again. Make sure it really does happen that way. You can't even obey that. The Eddington experiment, for example.
See, current research isn't settled. The jury is still out, if you will. It's why it's still being researched. But there are many.
There's nobody researching any of these fundamental questions. If they were, they would get down to it already. They would have repeated the Eddington experiment if there was anybody giving a damn. And they certainly would have figured out that the double slit experiment has nothing to do with waves by now, if they were doing any fundamental research, because they'd figure out that, oh yeah, it's about surfaces. Just count the surfaces, count how far apart they are, and you have all the information you need to figure out exactly what kind of pattern is possible.
Examples of debates throughout history that we can still learn from today if we understand sort of how people thought at the different times when certain...
Yes, what they believed. What kind of hokum, what kind of fake stories did they believe about the Messiah? And that's all this is. Do you believe that Jesus walked on water? Well, I guess if he walked on water, he must be the Son of God, because none of us can do that.
Evidence was...
You don't believe he walked on water, well, all of a sudden the story doesn't sound too impressive.
Lacking. Now, if you want me to cover, your favorite idea or debate in physics in this series, let me know in the comments, because I'll be doing these all month. But the one I first want to start with is one of the most famous debates.
All right, so anyway, there's just, again, this is just such a silly notion that there's any scrutiny applied in physics. You're either one of you or you're out, okay? You're either part of the collective or you're a dissident, you're an outsider, you're an outcast. You even did it to Einstein, as funny as that is, right? You did it to one of the creators of your woo, and you treated him like shit in the end.
Ever in the history of physics, right? It's about the nature of light itself. Is light a wave, or is light a particle?
Well, you're still treating him like shit in the sense that you're not paying any attention to what he actually said, and you're blaming him for things like gravitational waves and whatnot, things that he said didn't exist.
Ideas on the nature of light have been knocking around since, ancient philosophers, but we're going to start in the 1600s with René Descartes and Isaac Newton. In 1630, Descartes proposed the hypothesis that light is a wave, and treating light as a wave could explain everyday things like reflection and refraction of light. And then 40 years later, in 1670...
So this is really about a comparison between two theories of light, ray versus wave. It's really not, okay, wave-particle. It's ray-wave is the real debate. And because no matter what you make it out of, it obviously has to have some component to it. So you can't just say wave, right? I can make one water wave, right? There's a water wave. I made a water wave. Oops. I still have to remember. I have to do some of the logistics here. I can make one water wave. Okay, there. It's nothing. It doesn't mean anything, right? There's no frequency. Without a second wave, there's no frequency, right? I have to have two waves to have a frequency. And maybe I need even more, who knows, before something can tell exactly what the frequency is. And so if you're going to make a comparison to a particle model, obviously the particle model would have components also at a frequency, all right, bits. And clearly you have to account for what polarization is in this wave theory. Polarization isn't amplitude, it's something else. So somehow your wave has to have a shape. It has to have it this way, okay, of polarization. It has to have it that way, which is length and frequency. You have to have more components to it, and then it has to have a thinness, that's just incredibly small. And obviously I've proposed that it's obviously just like antennas produce light, radio waves, the same thing is happening. Antennas of matter are producing photons. And the photons are just bits moving parallel to each other, and that's their polarization, which is 1/2 of their wavelength, generally speaking. But it's a real thing, and so you haven't accounted for any of it. But the idea is look, a particle theory is just saying this. Compare this to this to this to this to this. What's this? Is that big a difference? No, it's not that big a difference. So obviously both theories are going to be able to account for certain behaviors as long as you recognize certain facts. And they've just ignored the facts. They pretend that surfaces are hard surfaces, that they're not made out of atoms. I could make a surface for an electron, and the electron's going to see a piece of steel here and a piece of steel here. The electron's not going to see electrons and protons. No, it's going to see just a straight line of steel. No, that's not what an electron sees. And they ought to know that. I shouldn't have to clarify that obvious fact.
Newton, who was a scientific giant at the time, right, famous for his ideas on gravity, proposed the idea that light is actually a particle, because only particles could describe the straight...
He called them corpuscles, which implies particle, of course, but yes, that it's clumpy. Same thing Feynman said. So Feynman agrees. It's clumpy. It's not a wave. Feynman overtly said it. None of you will account for that at all. He overtly said it, you know, in a videoed lecture. He overtly says, it's not a wave.
Lines that light travel in. But at the same time, you've got people like Hooke and Huygens who've come up with the maths to describe light as a wave and shown that.
So again, they didn't come up with maths to show it, so that's just, you know, she just threw that in for fun. They diagrammed it as a wave, but so what?
It could perfectly characterize things like reflection and refraction and diffraction again.
And so can you do it with particles? So you just make it particles, you make it rays instead of waves, and it works just fine because it's all about vectors. It's all about lines. So they're just saying the wave creates this line, and it creates this line, it creates this line. Well, obviously the wave creates all those lines. And all you're really saying is, no, what we see as light is a bunch of different components to it, and it's going in different photons, are going in different directions, and you can just follow one ray of light, and you get the same vectors. So again, it's just, this is almost a distinction without a difference.
Despite that, though, Newton's influence was just so strong at the time, and in the decades to follow as well, that his ideas of particles of light were just given so much more scientific weight.
So again, it should have just been rays of light. Clearly they travel in straight lines, these elements of light, and they land in very tiny locations.
But then there was a cat thrown amongst the pigeons with Thomas Young's double-slit experiment.
So again, nothing new. Newton had already done this experiment, you know, single slit. He'd also done this experiment, the single impediment. So he had done essentially the surfaces facing out and the surfaces facing in experiments. So that is the double slit, right? Two surfaces facing in, two surfaces facing out.
Of 1801. He sent a beam of light through two slits and produced this interference pattern, right, where light waves would add and subtract from each other in the way that only waves could.
Right, and it doesn't work. So he did it in this crude fashion, didn't use monochromatic light, used sunlight. Got a very crude image that we know isn't the real double slit pattern. The real pattern is more complicated. And even in his day, if you did the math, it doesn't work. The center of the openings, if you use that as the point sources, you won't get the right answer. You won't get the right size for the bars unless you use an infinitesimally small slit. So obviously you have no obligation rationally to use an infinitesimally small slit, right? There's no reason to think, oh, it only works, you know, if you have to confine the experiment to such an extreme circumstance to make it work, then aren't you conceding that you probably don't have the right answer because it doesn't fit the 999 circumstances? Right, if you only analyze elephants when they're on top of a round ball, you know, sitting on top of a round ball, you know, that's cheating the elephant, right? Because most of the time the elephant isn't standing on a little round ball, right? I mean, you can get this. So the simple argument is that Young's classical drawing of two waves won't give you the right answer because the point source, the distance, would be this distance, the distance between the two centers, okay? And it won't give you the right bar size. It will give you the, and again, we know this is on an arced screen, which also Young didn't do. Okay, you know, the only way you can do fair analysis is to have the equidistant, and then you'll know that this thing is traveling through space. This effect happens here, it happens here, it happens anywhere in distance, and if you do equidistant, then you understand it's a confined pattern. There's only so many of these little nodes in a 90-degree span, and that's all there is. And it's the same number if I'm a mile away or if I'm 2 inches away. I'll get the same number. All I can do is make them bigger and smaller based on distance. But this distance, this d, will not work. It won't give you the right answer. Okay, in the single slit, it's clearly understood. This d, the surfaces, the distance between the surfaces gets you the right answer. This vector plus this vector gets you the right answer. So we know the double slit has to be understood as being, these are the point sources, okay? The surfaces. This is a surface experiment. It's the single surface and the double surface and the quadruple surface, right? This is the double surface experiment, the single slit, and this is the quadruple, the four surface experiment. And the math that actually works, they'll get you the fancier pattern, you know, the pattern where there's a little deficit here, you know, no block where it should be. The math that works understands that these 2 points create the big pattern, the envelope. And these two surfaces create the size. This distance creates the size of the little blocks. That's the math that works. That's the truth. Young's analysis was completely wrong and completely incorrect. It's glaringly incorrect. It doesn't produce the real double slit pattern, and it doesn't produce the right single slit pattern. Now, the only circumstance where it does produce the right answer is for a kind of a sneaky reason. So you can understand, if I make the slits so tiny, just a tiny, tiny little opening, well, then the difference between this surface distance and this surface distance will be so small that it'll be negligible. So if I make this smaller than a wavelength, this opening, less than a wavelength, then I will create a mathematical circumstance where both patterns are the same, because the distances are the same. So the envelope pattern is going to be the same as the bar pattern, and so therefore I'll basically negate the difference between, I won't be able to see, there will still be a subtle difference, but it'll be so slight, the difference, that I won't be able to see it. Okay. Clearly, if they did the experiment carefully, they would see it, and they'd also recognize that even in infinitesimal size slits, they still have a difference. But the truth is, you can hide the truth by doing this. So every time they want to do the math for the double slit, they choose to do infinitesimally small slits so they can totally ignore these D numbers and just go with one D number, this distance, and just cheat the whole experiment. They're overtly doing it, okay? That's the overt truth. That's the facts. This description of reality is just crap. The Young experiment was completely unremarkable to somebody in hindsight. In hindsight, it was nothing. It was misinformation.
The same principle is used in noise cancelling headphones today, right? The headphones record the sound that's coming in, completely invert that sound wave, and add...
Right. I mean, Young was an audiophile. That was his expertise. So what? Again, so there's no indication of, this is the simplest pattern you can create, on and off. Why you're saying, oh, it must be the same as sound. Well, the fact is it doesn't work mathematically the same as sound. So you know it can't be, because it doesn't work. The waves are in the wrong place. The surfaces don't, a single slit in sound doesn't create the interference pattern. A single slit in water doesn't create the interference pattern. It does in light. Why? Because light has the point sources at the surfaces, where sound does this one big wave thing. Water does one big wave thing. Okay, light does 2 point sources, 2 waves right on the surface if you're going to use waves. But I'd argue it's not waves, it's scatter. Scatter looks just like a wave, right? If I put light in a different direction every millisecond, right? That looks like a wave, but it's not.
Them together so that they cancel each other out. It's the same thing that's happening in the double slit experiment, except it's the 2 waves.
So again, it's not the same thing. It's provably not the same thing. The math doesn't work. The drawing can't be drawn. It doesn't work. Nothing about it works. It doesn't make any sense. It's completely flawed, and yet they keep citing it.
Waves that come through the separate slits that interfere with each other, and where it's dark on the screen is where those waves have cancelled each other out.
So again, this isn't the classic double slit experiment at all. It's not the right image to show, because we know the correct double slit in monochromatic light, even in not monochromatic light, you'd still be able to see the get darker and then get brighter and then get darker again. So this is just a fraud, because we know the pattern extends, and we know the pattern goes from dark to bright again. We know there's an envelope.
It's bright on the screen is where they've added together to give you a stronger wave. Now you would think by this point everyone would realize.
And they also, quite obvious in that image, is the fact that the dark bands are much smaller than the bright bands. So proving in a sense that whatever this is causing this effect, it's disproportional. The destructive end is a lot less meaningful. It's a very small band. And the reconstruction is a very big band. And unlike their math, there's no evidence of a sine wave here. There's no evidence in light that it progressively gets lighter and progressively gets darker, there's every indication that it's either a photon or it's not a photon. It's either remade in a form that's recognized as a photon or it's not remade. And there is no evidence of any sine wave.
All the evidence was piling up in favor of light being a wave. But Thomas...
So there's not all this evidence. And again, so the point is clearly in hindsight, we know even if people could have been fooled, okay, and misunderstood, because they didn't see the real pattern and they didn't know all these other details, even though they didn't do the real math, really, right? I mean, the truth is you have to do the math wrong. So, and the fact that the thing to find is, where did they start using infinitesimally small slits? You know, where did that first be a conversation, where the slits had to be infinitesimally small? Because that's when, you know, that's when the chicanery, that's the shenanigans. Okay, when you start analyzing the experiment in a special circumstance and ignore all the other circumstances, because that's where the math that's the only place you can make it mathematically work, is with an infinitesimally small slit. As soon as you make the slit bigger than a wavelength, you're going to see the fact that your math gets the wrong answer.
Young didn't just do his double slit experiment with light. He did it with electrons as well.
So, I mean, this is such an insane statement. I mean, it's just, you're saying, how could this be how could she have a doctorate in physics and say something this, it's such a bizarre, I mean, not to know the context that we didn't have any control over electrons in 1801 or even in 1820. I mean, and to say that Young did an electron experiment, a slit experiment with electrons, how the hell, what did he use to do it with? I mean, it's just insane. I mean, electrons weren't even, you know, we didn't even know what X-rays were. I mean, it makes no sense. How could you possibly have done an electron experiment, you know, in 1810?
Well, the tiny particles that orbit the nucleus of atoms. Particles.
So again, she just said it as if it's the truth. It's not the truth. So obviously, the first electron experiment that had anything to do with the double slit is cited as the Bell Labs experiment in 1920. And it's not even close to a double slit experiment. I mean, yeah, I really should. This is a good enough time to get to it. But it's such an egregious, you know, error to cite that Young did any kind of electron experiments. That's just crazy. So what am I looking for? I got to turn this back on again. Okay. All right. So, so the electron experiment, 1920. So some scientists at Bell Labs just wanted to see what would happen to electrons. So they hit a piece of nickel with electrons straight on, and they just check at what angles they get, you know, what kind of scatter they get of the electrons. So how did the electrons scatter? And they were getting nothing remarkable. And then what happened is some air got into their experiment, oxidized their nickel, so they wanted to clean the nickel, so they heated it. And apparently when heating it, they realigned the crystals of the nickel. So now the crystals of the nickel were all lined up on top of each other. And so now when they did the experiment, okay, they got a peak at, say, 50 degrees. Okay, so they did the experiment and there would be more electrons went here than went here. And then more electrons, again, a little peak here and maybe a little peak here. Now, these peaks aren't anywhere proportional to what, you know, double slit. But anyway, so they're saying this is a double slit experiment because obviously what was happening is that you could argue the electron was going through the layers. And so some of the electrons would reflect off this layer, and some would reflect off this layer, and some would reflect off this layer. Now, the problem with that is obviously it has to be the same electron somehow, okay, to interfere with itself, kind of argument. And obviously these path lengths are going to be a huge problem. Electrons aren't composite objects. Their frequency isn't built out of some nodes and all of that stuff. Their wave wouldn't be made of components, and the components wouldn't be going to these different locations. So how could they ever arrive at a surface at the same time or at any place in space and interfere with themselves at the same time? I mean, these are definite path length differences. You can't change the fact that this electron that reflected off the top layer is going to be a lot further away than this one that reflected off the second layer, the third layer, the fourth layer. So, and what you could also know is that obviously this has to do with what the crystals line up, and obviously the atoms in the different layers of crystals would probably line up in a arrangement that is compatible. You know, where the protons are as far away from each other, and electrons, and they all have to be in balance. So there would be a certain geometry to how these crystals would line up, and that geometry would dictate that light coming in is going to have a certain probability to reflect at certain angles, based on the fact that these certain pressure points will exist, where, you know, if you hit the atom a certain way, it's going to push into the pressure of the crystal, and it's going to reflect in a certain way, and that there'll be a certain consistency, and that there'll be certain odds that at certain locations you get more light. So that's hardly a stretch. But anyway, this is in no way, they're saying this is a double slit experiment. Nothing goes through anything. There's no slits. It's just not a fair comparison. It's completely about reflections, okay? And reflections imply impacts and scatter. I mean, it was originally done as a scattering experiment, for fuck's sake. I mean, you just can't get away from the fact that it's a scatter experiment. So anyway, that's 1920. So obviously, back in 1801, he didn't do a better experiment than that, demonstrating electrons doing two-slit behavior, when it wasn't until Bell Labs did it in 1920. And again, it's not a double-slit experiment. It's not even close.
People knew that they were particles. They had been measured in labs as particles. And yet when Thomas Young fired these particles of electrons at the double slit,
so have light been measured in the same way, clumpy, as Feynman would say. So again, how we measure something is part of the argument here, is that most of this stuff has to be measured by seeing it move bigger things. We can't see the small snowballs until they move a big snowball. So everything's going to look clumpy because it's all about big snowballs moving, because that's the only thing we can understand, we can interpret, we can see.
they acted in the same way as light and somehow managed to interfere with each other to give that pattern of adding waves together.
Right, and somehow, and in some way, and blah, 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 blah. So even though they don't have a frequency, you can't recombine their phase because they don't have a phase. I mean, this is giving electrons, it's bad enough giving them a frequency, but to give them something called phase doesn't make any sense at all. How can they interfere with their own phase?
And cancelling waves out on the screen. So if electrons, which were particles, could make that pattern, then would that mean that also light that makes that pattern is particles, despite the fact that the way that the pattern has been made could only be understood if light and electrons were waves?
Right. So again, the simplest pattern in the universe, okay, on and then nothing and then on and then nothing and then on. You know, the simplest pattern you can make is some sort of on-off pattern. And they're saying it always has to be wave interference. There can't be any other explanation. So again, you can't shoot, I can't take a gun and shoot bullets. And then I certainly couldn't take my gun and move it when I shoot my bullets. And that certainly wouldn't create anything like a frequency in space of bullets. No, that couldn't possibly happen. Yeah, it can.
This was such a problem at the time that in 1818, the French Academy of Sciences actually launched a competition to try and find like the experiment to end all experiments to determine if light was a wave or a particle. Now, a chap called Fresnel, so apparently it's pronounced Fresnel, not Fresnel.
All right, so she edited the video to fix that, right? But she didn't fix the Young did the electron experiment. So she, two places says Young did an electron experiment, and she didn't fix that. That error is not egregious enough. But mispronouncing his name, that's egregious. So we'll fix that. But we won't fix that other obscenely silly error.
Oh, universe wept, Becky. Entered, who wasn't necessarily a physicist by training, but he came up with a very simple experiment to test this. He said if you have a beam of light and you put something in the way of that beam of light to block it, for example, just like a circular piece of card, depending how the light behaves going around that circular piece of card will tell you if it's a wave or a particle.
So it's really just a silly argument because we know that particles will deflect off of things. Now, the idea that they would deflect in, okay, that's the part that doesn't make any sense, right? So if I create a barrier, so I'm just saying that, you know, you can, these people didn't have nearly what we have now as contextual understanding. They didn't have this whole notion of atoms, electrons, protons. very small, little tiny objects, charges, and all the rest of it. They didn't have that context. So, you can't fault them for going a bit astray in their understanding. Okay, so conceptually, the argument is if I put a barrier, so let's just say it's a quarter, and it has a surface, you can understand how, well, something partically could hit and go this way. All right, that could happen, but there's no real explanation for why it would go this way. Where a waves like to fill in blanks, right? So waves are always trying to go around corners. So the wave theory makes sense because, yes, waves will try to go around the corner, okay, where a particle won't try. It'll just deflect, go this way, and that's it. That's, you can scatter this way, but you could never get any scatter in. Now, obviously, we have more understanding now. We know that the quarter has a surface, and the surface isn't just steel. The surface is this bubbling thing where little pieces of electrons and atoms and ions are all moving back and forth between the surface. The surface is a mix of substances, the atmosphere here and the stuff here, the atoms here, and that they're outgassing into each other. They're blending, and so it's a amorphous blob of active bubbling stuff, almost like the surface of the sun. And so that's what the electron is going to be passing through, is this active area of ions and electrons and stuff. And there's every reason to believe that it could deflect this way. Now, it's still more likely to go that way, but there's every reason to believe it can go this way. So again, a particle theory wouldn't have any problem in any modern understanding of what an object is, because modern people should know, modern physicists should know, there's no such thing as, look, the atoms make a straight surface. There's no there's no surfaces like that anywhere. No substance makes anything called a straight surface. It's always just electrons on the outside, okay? It always is. Electrons. They're always there. Always. I have to explain this to a doctor.
So if light was a particle, when you put the object in the way, you would just block all the light there and you would get a perfect shadow of that object. But if light was a wave...
So we already knew there were no perfect shadows. So again, what's the conversation? I already knew shadows were fuzzy, both ways.
When it hit the edges of that object, it would diffract, i.e. it would sort of disperse around the edges. And if that happens, it then disperses into the path where the shadow is blocking the light from upstream, and it would actually interfere with itself there.
Right, and it doesn't interfere with itself, but it's the same argument that it's just the same argument as the double slit. You have a distance, okay? Oh, jeez. Sorry. Oh, I didn't change it anyway, so I'm saved by the fact that I didn't fix it. All right, so the Arago spot, or whatever you want to call it. The idea is that there's the quarter. Let's say this is a quarter, and you're looking at it on its side, right? But if I did it round this way, you could understand that light's going to hit this side and this side, and light's going to hit this side and this side, and light's going to hit this side and this side, and those are all distances, right? So just like a single impediment or just like a single slit, those are just distances between the surface. So obviously, if I use a big thing like a quarter, you can understand this distance is gigantic in the sense of the number of wavelengths, and that the little bars of light are going to be so close together you'd never even ever see them. Okay. And the second problem is like there's not that much light that is going this way. Okay, it's less likely to go this way, and so you don't have much light in the first place. And so the rings, you're going to get Newton's rings. Newton's rings going out this way, and Newton's rings going the other way. And it's just really created by the fact that you're sending a contribution from here and you're sending a contribution from here, and those two will add up and create in phase. And that the idea would be is that you can go this distance with this distance, or this distance with this distance, and this distance, and those would be wavelength differences in the path. So anywhere there's a wavelength of difference means they're back in phase, and so that's where you're creating all of the circles. So the inside has circles, the outside has circles, and they're really, really small circles, really tight. because it's a big object. So I have to use a very small disk if I have any hope of seeing the rings. But the real point is that the same light will hit all of these areas proportionally, just like the slit experiments. And the fact is that the mean would be this, the Arago spot. And you're just basically saying that, you know, the difference is that this amount of light has to spread all over all of these surfaces. So all the angles coming from all these different places that you could send the light from, these two sides and this two sides and these two sides, they all have to spread over this big surface, where the center, all the light from the entire circumference, that is, the two contributors from here and here, the contributors from here and here, the contributors from here and here, will all hit the same one point in the center. So there's a bunch of photons hitting a tiny area, which means that you're likely to see the reflected light. So it's just about the fact that, yes, you'll see this reflected light, but the rings are still here. They're just very small and very faint. And they're all there. And they're all based on the same theory of just putting something back in phase. So again, it's not about destructive. It's just about reconstruction. All you're doing is rebuilding the phase of the photon. You scattered the bits of the photon. You scattered the waves, you could argue. And now you're going to reconstruct the phase. And when you don't reconstruct, you won't see a photon because it's not going to be a consistent frequency. It's not going to be red light or blue light. It's going to be mixing, and that mixture won't be seen as either, so to speak.
Now, this is the point that famous statistician Poisson enters the story, because Poisson had heard about this entry to the competition and essentially said it was absurd, because of course if you put an object in the way, it would just perfectly block the light. You wouldn't get diffraction, because if that was the case, you would end up with a bright point of light right in the center of where the shadow of your object should be. And that result would just be absurd, because that's not what we see in everyday life. And so therefore, we shouldn't even need to conduct the experiment, because if light was a wave, that result would be so absurd. But a member of the judging panel.
So again, there's nothing absurd about the argument, except understanding that the real argument is that particle theory, if you make the thing not in a composite object and you also forget that it's small stuff going through a medium, you would say there's no way it can deflect any other way than out. There's no way to hit the edge and have it go this way in. It can't hit the edge and go in. That's why particles wouldn't work. But obviously it will work if you understand it's not hitting any real surface. It's hitting an electron. That's what the light does. It hits electrons. And the electron does have the choice to move either way.
Francois Arago, who later ended up becoming Prime Minister of France, insisted that for scientific rigor's sake, this experiment had to be done. And lo and behold, when you do this experiment with monochromatic light, i.e. light that is all the same color and wavelength, so it can interfere.
So again, it doesn't matter. That's completely irrelevant. You don't have to do it with monochromatic light. The same principle exists. All the colors, blue, red, green, yellow, pink, it doesn't matter. Right, it's only three, but let's just say they all have to go to the same center. There's no other center. They all have to go to the same center. And they're going to go to the same center at all focal lengths. They're all going to have vectors that'll get there. So it just doesn't matter.
With itself properly, you get this bright spot of light.
All right, so it's obviously not very bright. So where she's pointing the arrow is the little spot. This is the disk. The black part is the disk. This is the diffraction going out. Okay, and this is the diffraction going in to the little tiny one spot that you see. So you don't see the rest of the rings because, number one, they're too small, and number two, they are spread over too much surface. So it's too little light spread over too much surface for us to see it, and only in the very center where all locations sent their contribution to the same place, that's why you see it. All the photons hit the same place.
In the center where that object should be casting a shadow. So the result of that experiment, once again, was against sort of the scientific legacy that Newton had left behind for, hundreds of years. And it was something that scientists at the time were quite wary of doing. It's easy for us to sort of look back with hindsight and say, look at all this evidence piling up in favor of light as a wave.
Yeah, in hindsight, we should look at the evidence and say just how bad it was. It was really bad evidence. Newton does the surface experiments. It takes 100 years before they decide to play a game with those notions again. And then again, Young's analysis is clearly corrupt. And it's made even more corrupt when they start saying, well, if it's an infinitesimally small slit, so it's smaller than a wavelength opening, because that's the only way the math works. I mean, clear evidence of chicanery, shenanigans. I mean, clear. That's what you should learn in hindsight, that a lot of quote mining of the evidence was being done, that there was a lot of cheating to make wave theory work. It wasn't working on its own. It wasn't working with integrity. It was only working if you cheated.
When you not see that and not claim that. But I guess it would be akin today to, claiming that Einstein was wrong about something. It's definitely possible that Einstein was wrong about something, but...
Yeah, unfortunately, he was wrong about just about everything. So again, the only thing he did right was to oppose the wrongs of quantum mechanics. But he had plenty of wrongs of his own. The whole bent space thing is a silly explanation. It's vacuous. There's no real energy involved. It's movement by a god. There's no evidence of any mover.
You can imagine the reaction of the scientific community and the world's media and the world if someone claims that. It's a very bold and brave claim, and you better be damn sure of it.
It doesn't matter. It doesn't matter whether you're damn sure. It doesn't matter whether you're fucking right. None of you people will listen. None of you people will accept any critiques of your physics. Anyone who even tries to bring up these subjects of how flawed the evidence is gets ridiculed and shut the hell up, okay? I've been kicked off of every science forum. Not for saying anything nasty to anybody or doing anything rude at all, just for asserting that you don't have evidence for what you're claiming.
Before you make that claim. But then later in the decade, in 1864, another scientific giant waded into the debate, James Clerk Maxwell. So Maxwell was studying electricity and magnetism, and he was trying to come up with equations to describe how electricity and magnetism works as a wave. And what he found was that those equations also perfectly described how light propagates through space.
Well, again, it's so silly because these equations are all vector based. They're all about drawing straight lines and seeing where the straight lines go. So it's all based on understanding the force as being completely proportional to traveling in a straight line to a location. So it's all about point A, point B, point C, and drawing straight lines between them. It's like gravity equations. It's all straight line vectors. And the only way you're representing a wave is this pretense that somehow it did everything at the same time, when clearly all these experiments take place in the context of watching groups of objects over time. And it can be understood that any one moment, they're not a group. Any one moment, they're all doing their individual thing. So this is understanding that every soldier in the wave of soldiers is an individual soldier taking his own path, eating his own little lunch, walking in his own little boots. There's no wave.
And also how light behaves as well. There's only one thing that he could conclude from that, and that was that light...
He had already concluded before, and it's what he believed, and he was a wavicist, okay? So it's that clear. And so... But there's no formula here. There's no wave in these equations. You can show the equation. There's no waves anywhere in here. All of these equations are based on understanding force traveling in straight lines. All of his drawings of charge are straight lines creating any curved line. So if there's a curved line somewhere, it was created by two straight lines.
Was a wave. With Maxwell's results, I think that was the sort of final nail in the coffin for scientists at the end.
So this is the term they use, nail in the coffin. Clearly, there's no wave formula. There's no wave in the mathematics. The mathematics are clearly made out of straight line vectors. So why is this nail in the coffin evidence? Oh, because you said it was waves. That's all. That's the only reason. That's it. Because they say so, not because the math indicates so.
Of the 1800s, in thinking that light was a particle. It was sort of around the time that everyone had come to the general agreement, okay, well, light is a wave, and that's when sort of everyone went off on a tangent trying to figure out the medium that light propagated through with the whole ether thing that I've talked on this.
Right, that's not really the truth. But anyway, obviously, Eddington and all the, the Michelson-Morley experiment was another. They had their own beliefs and their own reasoning, and it wasn't because of Maxwell. But anyway, go ahead. Continue.
Channel before. I'll link it in a video somewhere so you can go watch that. But ironically, as soon as the scientific community had started to accept this idea of light as a wave, is when the evidence started to pile up again in favor of light as a particle. So at the turn of the
So again, there's no piling up of evidence. There's very little evidence. It's very vague and very not very good and kind of fuzzy because it doesn't fit. Again, I'll just point out Young's analysis, obviously bad. And by the 1900s, it should have been well understood that it doesn't work mathematically. Two waves don't answer the question. The two waves that Young drew in the position he drew them don't work.
Entry in 1901, Max Planck showed that you could only explain the spectrum of light that you get from a glowing object, something we call a black body, if you quantize the energy being given off, i.e. you split it up into these discrete chunks of energy, and therefore you're treating light as a particle.
And it's just about the fact that we see light as a clump, okay? It's just a fact. Our brain is seeing electrons, electricity. It's not seeing photons. So to see a photon,
now, a lot of people are very impressed with
we have to see, okay, what it causes as an effect. We can't see the photon. We can only see the effect, and the effect is a clump.
Planck's work, but they sort of dismissed a lot of the models that he'd come up with and said they must be incomplete in some way. And if we do a proper full derivation without maybe some of the basic assumptions that Planck started with, then we'll end up in a scenario where we can actually explain this in terms of a wave, and we don't have to maybe...
Well, you could never explain it in terms of a wave, because you can never explain polarization of light with a wave. It just doesn't work in any way. How does a one electron, this tiny, tiny thing inside of one atom, ever create a whole photon when the photon is going to cover a huge amount of space, and it's always going to be the same amount of space? It's not going to be a varying amount of space. It's not going to get bigger as it goes further away. It's not going to do any of that. It's all in parallel space. Somehow an electron, this tiny thing, 1,000,000 times smaller than the polarization, is going to create an effect in some sort of ether that somehow that effect is going to have exactly the same dimensions as it travels, and it's a huge dimension. The polarization is giant. The fact that it doesn't work is obvious.
Split everything up into chunks, maybe some way our maths is limited. But then, in 1905, Albert Einstein comes along. He used Planck's model of these quantized energy chunks, these particles of light, to explain one of the most outstanding problems in physics at the time, the photoelectric effect. So you shine...
So she's going to get this wrong. I mean, you know, this is already settled science. This is really just the ionization effect. You ionize atoms, you're much more likely to ionize an atom with a higher frequency photon. So the higher the frequency, the more likelihood of ionizing atoms. And ionizing means you're moving electrons, right? You're displacing them, you're causing them, you're obviously negative ions are going to be the obvious thing you're going to create. You're going to shoot these electrons out of the substance and create negative ions. But the point is it's really just about the ionization effect, and ionization creates electricity in this circumstance.
Light onto, say, a sheet of metal, a collection of atoms, then those atoms give off electrons. Now, what's observed with the photoelectric effect is that the more light you shine on your atoms, the more electrons are released.
Right. See, this chart is way off. The real photoelectric effect is, I guess I should draw it. I mean, she's got it so wrong. And it's like, I shouldn't have to explain this to a doctor in physics or cosmology or whatever the fuck it is. Cosmetics. Anyway. Alright, so the look of the chart is correct, but the point is you do frequency this way. Alright, this way. Alright, and you do amount this way or something like that. And the point is there's a line, okay? Frequency. Here's red light. Doesn't work. Green light. Doesn't work. Blue light. Bingo. Now you start doing this. And the more you send, okay, and the higher the frequency, the more energy the electrons have. So if I go with a higher frequency, the line has a higher pitch or whatever. But that's the line. The line starts, this is the ionization. You start making ions here. That's the frequency that ejects electrons. And once you eject them, the higher the frequency, the faster they'll eject. Okay, so the more momentum they'll have when you eject them. So it's just about energy, really. It's about heat. Okay, so yes, the hotter you make it, the more likely it is electrons get pushed off the surface. But that's, she's got the line in the wrong place. I mean, the real subject, the meaning of the photoelectric effect is the fact that this line doesn't start at 0. It starts here at blue light. That's the meaning of the line.
And the higher frequency light you shine, the higher the energy of the electrons that are released. So you can shine a little bit of high frequency light and get a few high energy electrons, or you can shine a lot of low frequency light, like microwaves and radio waves, and you can get a lot of low energy electrons.
No, you don't get a lot of low energy electrons. That's the whole point. You don't get any electrons flying off the surface. So the effect doesn't happen until you have a high enough frequency. Now, they have figured out that if you really flood it with a ton of energy, you're going to get some electrons. But that's just because of, obviously, the more energy you throw at it, they're hitting it so often that some of those hits are going to look like, it's like if you only punch with one fist, you can only do so much. If you start punching with both fists, it could look like you hit somebody twice, in the same time. You could hit them with both fists at the same time, and that could look like a super punch.
Vice versa. Now that is not what you'd expect.
So you got these 3 charts that mean absolutely nothing, because again, the whole point of the chart is that it starts out here. You have to start out here. So, this is, I'm just frank, I've never seen it ever displayed this way. I'm just saying, I don't know whether anybody disagrees or they want to defend this, that somehow low intensity radiation will eject electrons and all that kind of crap, because that's not what I understand. What I understand is there's a certain point you get to ionization where you're actually breaking the atoms and knocking the electrons off, and you have to have a high enough frequency to do that. It's this whole get it out of the well thing. You have to have enough energy to get it out of the well, and my argument would be you have to have enough speed to tip it. It wants to go back really quick, right? It's on a very tight spring. So if you hit it, it springs right back. But if I hit it while it's over here, then I can break the spring. You get it? I mean, it's a tipping point argument. That's all it is. And she's not showing a tipping point argument here at all. So again, another complete failure to get the fundamental physics right. This is a complete failure. This is just overtly wrong. It's misinformation. It's incorrect, and it's a lot worse than pronouncing a guy's name wrong. So how come there isn't any annotation fixing this? It's wrong.
To see if light was a wave. If light was a wave, you would expect that the more high frequency light you shine in it, the more electrons you'd get out, i.e.
And you do. So again, she's got a completely, that's exactly, so that wasn't your expectation. Why would that be your expectation? Your expectation would be the more light I throw at it, the hotter it gets, the more shit that should fly off of it. And the fact is, it doesn't work unless I get to a high enough frequency. If the frequency is too low, it doesn't matter how much low energy heat I impose. I need to impose the heat in discrete tiny locations. And if I don't narrow the polarization, that's the other fact, right? The other fact that they never talk about is the polarization of blue light is smaller than the polarization of red light. And the fact is that all the energy of the blue light hits a much smaller part of the surface because the polarization is smaller. So obviously that might be the deciding element, is how tight the polarization is will tell you whether you can hit the same electron twice. And that's all this is about, is the odds of the photon actually hitting the electron twice with 2 of its components. And the more likely you are you hit the electron twice with 2 of your components, the narrower the polarization is.
The higher the frequency will be proportional to the number of electrons out rather than the energy of the electrons you get out.
So again, the energy increases with the increase in energy, but has nothing to do with the effect. The effect is about the fact that low frequency light doesn't ionize.
So here again was another result that suggested that light was a particle and not a wave, finally, after the scientific community had seemed to come to agreement that light was a wave. Now, here's where Einstein's great leap came from. He said, perhaps it's not a particle. Perhaps it's only sometimes a particle.
All right, so I don't think Einstein said that. And the only time he did say it, conceded in like 1930-something or 40-something, was because of the ridicule he was getting for being not compliant. So he made some little statement about, well, sometimes it's like a wave and sometimes it's like a particle. La 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 la. Okay, can I be friends now? That's what it was.
And it was this idea, along with using Planck's model to mathematically explain the photoelectric effect, that won Einstein his only Nobel Prize. It was for this and not for relativity. Einstein also realized at the time, though, that if light was found in these quantized chunks of energy, these particles of light, sometimes at least.
So again, the other problem with this is that the only way we can detect light is with a clump detector. We can only detect when the big snowball rolls. We can't detect anything else. We have to detect electricity. We have to detect a phenomenon that's not a photon. And so obviously the little things causing the big thing to move, we can't say too much about them watching the big thing move. We can't say how many there are. I can't say a lot of things. So I mean, it's just kind of stupid to say, yes, it looks like it's clumps, because obviously we're looking with a clump detector. It can only detect clumps.
Then you should be able to measure the momentum of these particles. And in 1923, Compton managed to do just that, and it won him a Nobel Prize a couple of years later in 1927. He managed...
Well, again, the momentum is just the velocity, and we already knew that, so that's nothing. So it doesn't tell you anything. So this momentum argument really just has to do, again, with this perversion of a notion of what frequency is. And yes, frequency matters. When you're hitting something, it matters. All right, so I could argue that the Compton experiments, they just pervert everything into this nonsense. It's just they just don't care about the details. Compton's measuring scatter. So he's measuring, that was his big subject, was scatter. Okay, how do photons interact with media, stuff in their way, atoms, whatnot. And so the idea would be is you send a photon into a field of substance and you see what happens to the photon, okay? And the simple argument to make to you is that, yes, you'd see this change in the energy, a little bit of a loss of momentum, loss of total energy in terms of frequency. So you're just changing something that went in doing this and it comes out, I'm exaggerating, doing this. Well, you can't see that, right? No, you can't. Sorry about that. Gonna go up. Not without screwing everything up, you can't. Right there. Now I go over here. Oh, fuck. I needed that. Let's see, where you go? Hello? Mr. Chalk, where did you go, fella? Oh, there you are. Yeah, I found a bonus piece. Cool. Extra piece of pink. All right, so so this is what he was measuring, okay? That there would be a slight change in frequency, which implies a change in momentum, like somehow you used up some energy, and in a way you did, okay? But the truth of the matter is what is happening when you're hitting an atom is you're hitting an electron, you're scattering the energy, and the simple mechanism you can understand is that the higher the frequency the light is that's going in, that means the narrower the polarization. That means if it was made out of composites, like waves, okay, of elements, you could understand that I'm more likely to hit this one electron with those elements if this polarization is narrow. If this polarization is wide, I'm less likely to hit the same electron and to have an interaction. And so that was part of the theory, is that these small particles are going to absorb light very differentially. Okay, some are going to they're going to interact with this light a lot more often and a lot more aggressively than they'll interact with this light, because they can't do this hit the same electron twice thing if they're widely polarized. So those kind of relationships existed, but this again isn't really measuring the momentum of light. It's measuring the fact that the components of light, the fact is that frequency matters in the sense that the smaller the frequency, that means there's more of the stuff in the same amount of space. Higher frequency means more stuff in a smaller space. Duh.
to experimentally measure in a lab the momentum of a chunk or a particle of light, which eventually came to be dubbed photons. Now, this was all happening against the
So he really didn't do that.
backdrop of quantum physics and quantum mechanics. So Heisenberg in 1926 had proposed this idea of his uncertainty principle, that the more precisely you know a particle's position, the less precisely that you can know its momentum, and vice versa. Now,
And that started the rule thing. This rule thing that everything you can't know anything about anything because everything is amorphous and superimposed. And then Einstein made the counter argument, which led to them creating entanglement. So Einstein makes the rational argument that right and left hand gloves, if I send them out into space, then I'm going to know special information about this thing no matter where it is, no matter what confinement it's in, or no matter what else I know about it. I'll automatically know it's right-handed, right? If this is left-handed, I'll know this is right-handed. And that simple argument was perverted into, oh yeah, there is entanglement, and there's no right and left hand though. No, they don't know what they are until you look at one of them.
and then proposed
Silly. And it still doesn't even defeat the argument Einstein's making, which is you can have information that you're supposed to be incapable of knowing. So it didn't even answer the question, and they perverted what he said into magic.
the idea that underpins the entirety of quantum physics as we know it today. And that is the idea that the nature of atoms or particles themselves is governed by probabilities alone and not by any property of the particle itself. It basically has no say in what happens to it.
Right. So it's not a physical universe. It's not made out of physical properties. Things aren't having real location. So it's just magic physics. It's mush. It's bullshit. It's nonsense. Obviously, the causes are there, and they're small and discrete, and yes, they're hard to see, but we can understand that there are explanations where you do not have to give up on the fact that there are properties. They have real properties. There's real reasons why you roll the dice and there's a 6 on the dice face. It didn't happen by magic. It didn't happen because there's some sort of magic random god. None of that stuff has to be believed. It doesn't have to be believed. You don't have to believe that silly story, and the evidence really doesn't indicate that's the truth.
Now, Einstein hated this idea, and it's where his famous quote comes from. In 1926, he wrote a letter to Max Born, and he said, "I, at any rate, am convinced that he does not play dice." So at this point in the 20th century...
Right, and he's also convinced that the moon's there when he's not looking at it.
Physicists were essentially at their wits' end, because here was all this evidence that had piled up in the previous century that light was a wave. And then here was all this new evidence that was coming out of the birth of quantum physics that was sort of revolutionizing every other field that said that light was a particle. So they called a meeting of some of the greatest minds of the 20th century to try and get to the bottom of this. The 5th Solvay conference was held in October in 1927 to discuss the problem of the nature of electrons and photons. Now, it's probably one of the most famous physics conferences ever held, because 15 of the 29 people who went either had won or eventually won a Nobel Prize, including...
Right, and what does that even mean, right? Because we know these Nobel Prizes are given away for fancy, silly crap most of the time. And frankly, if they're all wrong, which I think is going to be provable, they're not going to mean much. Now, certain prizes were earned by actually discovering something real, not proposing something phantasmagorical and silly.
Marie Curie, who had won 2 by that point, 1 in chemistry and 1 in physics. It included Schrödinger, Pauli, Heisenberg, Bragg, Dirac, Compton, de Broglie, Born, Bohr, Planck, Curie, Lorentz, and Einstein. It feels like a physicist's dream, right? You know that sort of question where it's like, who would you invite to a dinner party, like alive or dead? It could be anybody. Or physicists just respond with like, the 5th Solvay conference.
Yeah, I don't know why, because none of them were terribly interesting personalities, frankly.
That's who I'd invite, just all 29 of them. That would be the most...
I mean, the little tiny bits of Einstein that's recorded are pretty meek. I mean, it's just his arguments are pretty meek and boring.
Incredible room to be in. So his minds gathered to try and come up with a hypothesis to explain why in some experiments light was observed to behave like a wave, and in other experiments light was observed to behave like a particle.
Right, so it doesn't behave like a wave unless you pervert the physical circumstance. So again, the Young experiment is now 100 years old, more than 100 years old. Plenty of time to analyze the math and figure out it doesn't work. 2 waves don't make the right numbers. So why are you still believing it?
Cool. And it was here that Niels Bohr proposed his rather controversial idea, at the start anyway, that the equations that we had to describe light as a wave described where you could find a particle of light yet it didn't exist until you went looking for it. The very act of observing the light causes the photons to exist. In Bohr's own words, the photons have no independent reality.
So this really is, he really was asserting that our consciousness is controlling, that it really was about humans observing. It wasn't just about this idea of observation, because obviously he knew that everything's being observed all the time by interactions. Because we don't have the tape recorder on doesn't mean sound isn't being made, right? I mean, so there's lots of interactions happening every trillionth of a second around you. There's interactions. So, I mean, I can't even say double trillionth of a second. I mean, you know, the rate at which things are being interacted with is insanely fast. And so nothing could ever stay in a superposition for very long because it's being measured all the time. It's being seen by something all the time. People's cell phones are seeing me all the time in the sense that they're deconstructing me. I'm decohering, constantly breaking down and having to be in one place to receive that interaction. The interaction is exposing me as being in one place. I mean, so this is all just such babble.
In the physical sense. But Bohr didn't stop there though. He said the same is true for electrons. Electrons only exist as particles when we observe that they...
So again, when we observe, the particle is traveling through the sea of energy all the time. It can't go anywhere without always being told, you have to be somewhere, you have to be somewhere, because I'm going to hit you, 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 I'm going to hit you. It's constantly being told, you have to be somewhere because I'm going to fucking hit you. And I can't hit you unless I'm somewhere, for fuck's sake. You know, I can't hit something if I'm not somewhere to do it. Oh, it's just too stupid. How do superimposed particles hit superimposed particles? I mean, it just gets to be so wacky. Why do you people believe this shit? I mean, why do I have to even make these videos? Can't you just on the face of it say, what sense does that make? So I'm going to see it with pieces of chalk that don't know where they are, right? I'm going to throw the piece of chalk that doesn't know where it is at the piece of chalk that doesn't know where it is. And they're going to be somewhere when they hit each other by some what? You know, I mean, that's just... Oh, you know, I dropped the chalk twice. I guess I got some sort of drop the chalk condition.
Are there. Otherwise, they can be explained as a wave, using the wave equations that quantum mechanics had so beautifully put to...
So again, there's no wave equations. It's just a nonsense. There's equations that dissect the locations of all kinds of things, and then you just do your vector math. So it's just like, there's no wave equation for gravity. Gravity is not made out of waves, blah, 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 blah. It's straight-line vectors of assumed force, and that's it. You add up the directions of the momentum. You don't add up any waves.
Produced to explain the orbits of electrons around the nucleus of atoms. This could explain why we could measure the properties of electrons in a lab and why Compton could measure the momentum of a photon of light, a particle of light, but also that Thomas Young could get an interference pattern from particles of electrons and particles of light acting like...
Okay, so she said it again, right? So, you know, what the fuck? Electrons. No chance. Again, you can't even theoretically build a two-slit experiment for electrons. It's impossible to confine an electron. Silly.
A wave when they were put through his double-slit experiment and producing this interference pattern. You know, he didn't actually observe which slit that the photon or the electron...
I mean, you're talking about a slit by the electron's supposed frequency. You would talk about a slit that would be something like 1.5 atoms wide. Yeah, we did that. Sure, no problem.
Electron would go through, and therefore they could act like a wave. It's something that's come to be known as wave-particle duality, i.e. light or electrons or protons, whatever, can be both waves and particles.
Whatever. What they can be is understood as timed events that take time to happen. So it takes time to make a photon, it takes time to receive a photon, because it happens because it has a frequency. It has to do this. And my point would be is, the fact is it has to do this to one electron. And the odds of it hitting one electron require it to be rather substantial. in terms of it has to try more than once. It has to have more than one component to have odds where it makes it possible to hit the electron twice.
Depending on whether you observe them or not. Einstein was vehemently against this idea, though, the same way that he was about the probabilistic nature of quantum mechanics, right? He said that an electron was an electron, no matter whether someone was looking at it or not, right? That
yes, and a photon is a photon, whether somebody's looking at it too. And they, again, I could go back to the electromagnetic radiation argument. The radio waves all are antenna biased. They all need antennas, and they all need a certain length of antenna. And this is all important to their function and to the capacity for them to be created and be effective. And the same is true for light. Light has a polarization, an antenna polarization, because it's made by atoms stimulated by electricity.
It was always there, wherever there happened to be. And so after this conference, Einstein and Bohr really sort of entered into this decade-long debate over this. It was Einstein's skepticism and his doubt over this idea, this wave-particle duality, and quantum mechanics as a whole, that really allowed Bohr and the other sort of, founding parents of quantum physics to really make sure that their ideas were concrete. Einstein would point out holes and places that didn't make sense in his correspondence with Bohr, so that the ideas that they were developing through that sort of first half of the 20th century really became such a founding sort of pillar on which physics stands.
They actually weren't arguing in any kind of rational way, in the sense they were arguing in formal paper form. So they would submit papers on these subjects, it wasn't a rational way to argue.
Today, with this accepted theory of the wave particle
and all thought experiments rather than any citation to actual experiments.
Duality nature of light, that I think there's no physics student of recent times that's gone through a physics degree and not learned about this incredible idea. It was
right, and so she got all these facts wrong, and this is her. She likes this subject. This is the subject to pay attention to, and she got it all wrong.
One of my favorite parts of my physics degree, and I think it's wonderful not only to
see. Her favorite part was looking at the young electron experiment. It was fascinating. He made it out of a cardboard. Yeah. Cardboard box. The electron gun.
Know the physics, but also to know the history behind this idea as well, because that history can teach us so much about how we should approach science today, right?
Right. The history is that a small group of people get to decide what the truth is. A tiny group of people are the inside, and everybody else is on the outside. And if you're at all non-compliant with what the group says, what the convention of cardinals decide what the religion is, and if you're non-compliant, well, then you have to create your own religion.
We should approach it with an open mind.
Yes, well, where's there any indication? Your propaganda is so layered and so thick. There's no indication that you care about the truth. There's every indication you care about validating your wave theory. And that's it. Force the evidence to fit. Create some infinitesimal slit. Yeah, okay, it works if the math works if it's an infinitesimal slit. That's not an obvious gimmick, an obvious bit of chicanery, an obvious bit of nonsense, an obvious bit of, well, it'll fool the average dumbass. The average dumbass won't recognize that we just stole his money. We stole the truth. We broke it.
All the evidence that's available, and a very healthy dose of skepticism.
And you have none of that. There's absolutely no evidence of any skepticism whatsoever. None whatsoever. I mean, it's just, you just get away with it all. The asshole says, we did it. And you say, oh yeah, there's black holes, they collided, they converted mass into bent space, whatever the fuck that is, by whatever process that is. Not regular radiation, not real radiation, no, just bent space radiation. And we measured 1/10,000th of the distance of the width of a proton. Yeah, we did that. Where's your skepticism? You don't have any skepticism. These are outlandish claims, and you just sit there and say, sure, tell me some more stories. I love these stories.
Just a quick note before I go. I'm going to be shifting the day that I post videos from Wednesday to Thursday. So just so you know, when nothing pops up next Wednesday.
Right. So they can understand physics, but they can't understand, oh, your video isn't on the right day. I don't know what to do. I'm totally confused. Tell us to like and subscribe.
That's why. Okay. Bye. and managed to show that it perfectly described, again, things like refraction, and diffraction. I just said refraction twice, didn't I?
So it's all a bunch of clips. She can't, she can't have a real conversation with you. She has to do it in a bunch of jump cuts. Make a 6-hour video and then cut it down. But anyway, I just hate this planet. There's good reason, right? I mean, the evidence is stacking up, right? Am I not stacking the evidence up that there's every good reason for any rational person to just go, oh, fuck, am I in shit? This is a hopelessly stupid place to be. They're all stupid. And they're liars. There's stupid lies they tell. Infinitesimal slit works. Yeah, nothing else works, but just the infinitesimal ones do. Is that proof? The Eddington experiment, that's proof, right? I mean, it's only 100 years old. Yeah, so what? We have all this space technology, and so what? The resolution's 400 times better. 400 times better resolution from space. About, it takes so much, hey, 10 minutes? We don't got 10 minutes. 10 minutes of satellite time? Oh, no, we can't afford that. There's nothing those satellites are doing that isn't vitally important every millisecond. We can't afford to sit there and, look at something else for 10 minutes. Fuck. You people. So disappointing. People fall for this crap. So anyway, $1,500. I mean, let's say if Dr. Becky is listening, $1,500 I'm offering, for you to endure an hour of interrogation on your silly physics and the real evidence that doesn't demonstrate any of this stuff. Just how weak your evidence is, and just see if you will admit, oh yeah, we're based all of this assertions we make about the truth based on really mushy and shitty evidence.